connected to the wireless network. And that's the focus in this area of our discussion. What we're going to do is focus on the 802.11 architectures, which involve first locating a wireless LAN, also identifying what are known as the SSIDs for an access point and how a client uses these, how a client makes use of beacons, which are known as beacon frames, and also the differences between passive scanning and active scanning for clients in a wireless LAN. When you install, configure, and finally start up a wireless LAN client, such as any of your USB or PCMCA card clients, the client will automatically listen to see if there's a wireless LAN within range. The client is also trying to discover if the client is also discovering at this time whether or not it's going to be able to associate with that wireless LAN. This process of listening is known as scanning. Scanning occurs before any other process, since scanning is really how the client finds the network in the first place. Both types of scanning, passive and active scanning, can be used. But in finding an access point, client stations kind of follow a trail of breadcrumbs that have been left by the access point. It's really the easiest way to think about it. These breadcrumbs are called service set identifiers and beacons, and this is the true magic behind locating a wireless LAN in the first place. These tools will serve as a means for a client station to find any and all access points that exist on the network. The first breadcrumb that we have to look at is the SSID. The SSID, or Service Set Identifier, is a unique, case-sensitive, alphanumeric value that will range from 2 to 32 characters. This is used by wireless LANs as really a network name. The naming handle itself is used for segmenting networks, as a rudimentary security measure, or in the process of joining a network. It's actually something that every single access point is going to have. The SSID is sent in a beacon frame, in a probe request frame, in a probe response frame, and in other types of frames that wireless access points are designed to send. A client station must be configured for the correct SSID in order to join a network. And this is actually your job. The administrator has to configure the SSID, which is sometimes referred to as the eSSID, in each access point. Some clients have the ability to use any SSID value instead of only one that's manually specified by you. But if clients are to roam seamlessly among a group of access points, the clients and all access points in the environment must be configured with exactly the same SSID. And this is a very important thing. The most important concept with a service set identifier is that it must match exactly between access points and clients. This particular number, or this particular value, being case sensitive and alphanumeric, you've got to be very, very careful on your characters or you will not get association. The other thing that's incredibly important about the service set identifier is that you never confuse it with the basic service set identifier, which is a 6-byte hexadecimal number that identifies the access point of frame origination or where a frame might have been relayed from. Whereas the SSID and the eSSID are interchangeable terms that denote the network name or the identifier of an access point. The basic service set ID is something that's internal to the access point that is not actually sent out as part of the association process for a client. Another major factor in the way that clients will find access points and actually be able to make connections is the use of what are known as beacons. Beacons, short for a beacon management frame, are very short frames that are sent from the access point to stations in infrastructure mode or station to station in ad hoc mode in order to organize and synchronize wireless communication on the wireless LAN. Now they do serve several different functions. One function is time synchronization. Beacons will actually synchronize clients by way of a physical timestamp at the exact moment of transmission. When the client receives the beacon, it changes its own clock to reflect the clock of the access point. Once this change is made, the two clocks are synchronized. Synchronizing the clocks of communicating units will ensure that all of the time-sensitive functions, such as hopping in frequency hopping spread spectrum systems, are performed without any type of error. The beacon also contains a beacon interval, which informs stations how often to expect the beacon from that point forward. In addition, beacons are responsible for containing information geared towards the FH or DS parameter sets. This information is geared towards the spread spectrum technology that we actually see the access point using, depending upon what standard it's supporting. A good example, in a frequency hopping spread spectrum system, hop and dwell time parameters and hop sequences are always included in the beacon. In a DSSS system, the beacon contains channel information that needs to be used. Beacons also contain the SSID information, and stations look inside of beacon frames for the SSID of the network that they wish to join. When this information is found, the station will look at the MAC address of where the beacon originated, and it will actually send an authentication request in hopes of associating with that access point. If a station is set to accept any SSID, then the station will attempt to join the network through the first access point that sends the beacon, or the one that has the strongest signal strength if there happens to be multiples. Another thing that is the responsibility of beacon management frames is the TIM, or Traffic Indication Map. The TIM is used as an indicator for sleeping stations where they might actually have packets that are queued at an access point from another station. This information is always passed in each beacon to all associated stations on the network. So while sleeping, a synchronized station can power up the receiver, listen for the beacon, check the TIM to see if they're listed, and then, if they're not listed, they can power down their receivers and continue sleeping. However, if they are listed in the traffic indication map, they can go out and retrieve any of the frames that have been queued at the access point. With wireless networks, there's also many supported speeds depending upon what standard of hardware that you have in use. We know that an 802.11b compliant device supports not only the 11 megabit, but also 5.5, 2, and 1 megabit speeds. This capability information is also passed in the beacons to always inform the stations what speeds are supported on the access point. There's a lot more information that's also passed within beacons, but everything in this list covers what is necessary from an administrator's point of view to be able to properly find any problems that exist in your wireless network. We also need to compare the two different types of scanning that a system will do. Passive scanning is simply the process of listening for beacons on each channel for a specified period of time after the station is initialized. These beacons are always sent by access points in infrastructure mode or sent by client stations in ad hoc mode, and the scanning station catalogs characteristics about the access point or stations based upon the beacons that it receives. The station searching for a network listens for beacons until it hears a beacon listing, the SSID that it was looking for, or for the network that it wishes to join. The station will then attempt to join the network through the access point that actually sent the beacon. In configurations where you have many different access points, the SSID of the network the station wishes to join may be broadcast by more than one of these access points overall. In this situation, your station really makes a good decision as it attempts to join the network through the access point that has the strongest signal and the lowest bit error rate. In addition, stations will continue passive scanning even after association to an access point has completed its process. Passive scanning will save time reconnecting to the network if the client is suddenly disconnected for some reason or disassociated from the access point from which they're currently connected. By maintaining all of this information in a list, it provides the access lists and their characteristics, and the stations are quickly able to locate the best access point should its current connection be broken for any reason, such as if you're moving around. And that means that roaming can become automatic with passive scanning. Automatically, when stations move around from one access point to the other, as one radio signal drops low, a station will automatically associate with another access point in its list and be able to automatically roam so that they can stay connected to the network. Stations will always use this information obtained through passive scanning for locating the next best access point, or ad hoc network in some cases, for connectivity back in. But for this reason, it's very important that as a wireless LAN administrator, that you always overlap access points, normally between 20 and 30%. This overlap will allow stations to seamlessly roam between access points while disconnecting and reconnecting without the user's knowledge. And of course, that makes it much more transparent to the user. They won't even know that they've disconnected. Identifying what 20 to 30% is going to be in your own environment is going to be the result of your site survey. Your site survey will actually identify how many access points you will require, the channels, and how you can make sure that you do have an overlap of this particular percentage. The other type of scanning that we have is known as active scanning. Active scanning involves the sending of a probe request frame from a wireless station. Now, stations send this probe frame when they're actively seeking a network to join. The probe frame will normally contain either the SSID of the network that they wish to join or a broadcast SSID. If a probe request is sent specifying a service set identifier, then only access points that are servicing that particular SSID will respond with a probe response frame. If a probe request frame is